Hello everyone. I would like to talk a little bit about security and design. Let's begin right here, which is that oftentimes in the networking world, we're told that we need to build security in from day one. We need to design the network in a way that it is secure. But what does security in from day one actually mean? Like, how do we actually do this? Isn't doing security just a matter of putting firewalls in the right places or whatever the case might happen to be, packet filters or whatever in the right places? Well, there are three thoughts that you can push back on this kind of mentality with and think about doing security from day one or building security into the design. The first is to build simple. Now, of course, I'm a huge advocate of getting rid of complexity where you can, so this is not going to be a big surprise coming from me. The second is building places for policy. So intentionally setting aside places in the network where you can put policy in place, and then build measurable. Really build in the telemetry that you might need for security from day one. Think about where you would measure and why you would measure. So here's a quote from Bruce Schneier, which is about complexity and security. He says, "The internet and all the systems we build today are getting more complex at a rate that is faster than we are capable of matching." And that is absolutely true. Security in reality is actually improving. So what Bruce Schneier is saying here is that we are getting better at security, but the target is constantly shifting. So we're getting better at hitting the target, but the target's getting narrower, smaller, and moving around on us. As complexity grows, we are losing ground. So complexity, therefore, is the enemy of security. But why? Let's talk about why that might happen to be. Let's begin here with that thought, which is that what we can think about in the networking world for complexity is we can think about a three-way trade-off: state, optimization, and surfaces. If you've ever heard me present on complexity or any other topic, I tend to bring these things in a lot, this three-way trade-off. So when I talk about surfaces, though, a lot of people don't totally understand what I'm saying when I talk about a surface. So interaction surfaces have two ways of being measured or to be thought about. The first is the breadth of the interaction surface. So the two systems that interact over a broad interaction surface interact in a lot of different places. As you can see, there's a lot of arrows that run between these two. The second thing is that there is a depth of interaction surfaces. So the deeper the two systems interact in terms of using state from the other system in order to do something locally within the system, the deeper that interaction surface is. So this illustration shows you two different systems that are interacting with one another through a single interaction surface, but they are deeply doing so. They're not very broad. There's not a lot of places, but they're very deep. So up here we have two systems that are not only broadly interacting, but they're also deeply interacting. Now, what we want to get to is we want to get to a system that is only interacting very narrowly and as shallowly as possible, with as much shallow interaction as possible. Why? Because the broader and deeper the interaction surfaces, the tighter the binding between the two systems. If you have two systems that are tightly bound, what you've done is you've enabled cross-system attacks in ways that you may not expect. Another thing is the more there are these interaction surfaces in here, these places where these two systems interact, you get a larger and richer attack surface. So broader interaction surfaces give you a larger attack surface, and deeper interaction surfaces give you a richer attack surface. So what you really want to get to as a rule of thumb is to have these two systems to be hermetically sealed where they're not able to interact with one another. Of course, that's irrational, or that's not possible in the networking world, because otherwise you wouldn't have the two systems there in the first place. Now, if we talk about the way a particular system is designed from the outside and the inside, from the outside, it looks like an opaque box. The system just looks like something that I can push inputs into and I get outputs out of, or push inputs into up here and down here, and I get them out on the top. So I can think of those outputs as being sort of a reshaping of the system, or my exterior view of that system. So it's an opaque box that I can push on and make things go in a certain way. Now, what happens, however, is that while I might expect if I push here on the system, I get a nice, even parallel push on the outside so I get the data out that I'm expecting. In real life, what I have is a lot of unintended consequences. If I push over here, I actually get something that's coming out in a different place than I expected. This is an unintended consequence. This is a mismatch between the way the system works and the way you think it works. So the more complex this system is, the more likely you are to have this situation where there's a mismatch between what you think it does and what it actually does. So this is something, what we would call this technical debt, actually. This is a form of technical debt in our systems, that we think it works one way and it actually works a different way. And one way you solve the technical debt problem in coding is you refactor the system so that you match your expectations to the actual operation of that system. So every unintended consequence that I get into is an attack surface. If I can attack a device or a system by pushing on it in a particular place, by feeding it data and having the result be something you don't expect as an administrator or an operator, then I've actually opened an attack surface in your network. So one thing I can do is I can simplify these systems to reduce the unintended consequences, which means in two directions. First of all, that I actually understand how the system works. So I'm expecting this sideways output from the input. And the second is to control the output to be more parallel to what I think I'm actually should be getting. So another point that you get into with good interaction surfaces is that policy containment is very, very key to security. I want to contain my policy within a module or to an interaction surface. The reason I want to do this is the more I have my policy encapsulated within this system, or the more I have it encapsulated along this interaction surface, the easier it is for me to understand and pin down what that policy is doing. There's something here called the subsidiarity principle as well. This is kind of an extended version of the subsidiarity principle instead of the social part of it, which usually is the subsidiarity principle says that what I want to do is I want to pull my decision making to the closest point that has the information about making that decision. You would normally apply this to government, to governance, to social structures, things like that. Within a network, what this might mean is it might mean I want to say that if this module has the information required to make a policy decision, I want to make that policy decision in this module rather than in a separate module through an interaction surface. So this is just a way of trying to simplify things as much as possible. So let's talk about places for measuring. Measurement requires context. So we need to know when we're measuring something what normal looks like. This is where people miss it a lot of times when they're troubleshooting or dealing with security, is they think I can just measure this and I don't really need to know what normal looks like. But it often happens that if you don't know what normal looks like, you don't know why it's broken or why it's insecure, what the attacker is doing. You just kind of guess based on background knowledge or rules of thumb or something like that. So you need to be able to measure what normal looks like, and then you need to know why normal looks that way, or rather how this system works internally. So having these clear interaction surfaces with shallow and narrow interaction surfaces or interactions between these systems allows me to better understand what I should be measuring. The more places I need to measure, and the more these measurements are deep measurements, the less able I am to do effective telemetry to understand exactly what's going on and what I'm trading off in having those types of things. So we normally reduce complexity via modularization. You've probably heard me say this 1,000 times, but there's this concept of the wasp waste. And what I have here is I have a typical wasp or a bee, and this particular bee or wasp has a lot of complexity down here. There's a stinger and there's a stomach and all these other things. And then a lot of complexity here. There's a lot of muscle structure to support those wings and the legs and digestive systems and stuff like that. So these are separated by this little wasp waste. And this wasp waste is a containment mechanism. So I can do the same thing in my network. I actually control complexity by inserting these interaction surfaces and modularizing what I'm doing. What's interesting is this modularization point also gives us places to insert policy and places to measure things. So my modularization that I'm already doing to reduce complexity, and again, complexity is the enemy of security, is also helping me in security. So let's think about how this might work in a data center fabric, let's say. So let's think about in a data center fabric, what we normally think about in terms of modularization might be my pods or something like this. And I might think in a normal hierarchical network or in a normal network design, I'm thinking about having 3 layers, and I might have my access layer, or 2 layers. I might have my access distribution and then my core, or I might have 2 layers, which are like just my access or aggregation and core or something like this. And what I'm doing is I'm doing aggregation, route aggregation, probably in my second or third layer or along the lines between these layers in order to reduce complexity and to modularize the network. In a data center, this bottom layer fabric is often a single flat failure domain. Now, I might be running BGP or a link state protocol or whatever on that fabric, but it's largely going to be, as an underlay, it's going to be a single failure domain. So what I need to do in a data center environment is, rather than modularizing horizontally, I modularize vertically. So my underlay is one failure domain, and then I may have a a network overlay, and say this might be EVPN sitting here, and it's going to be my second module. And then I may have an application overlay that sits on top of this, maybe running SXT or whatever the case might happen to be, Kafka or whatever it is, Kubernetes or whatever, that is going to give me my third layer. So what I'm doing is I'm modularizing in order to simplify. But what this also does is this allows me to break these up not into failure domains, but they also breaks them up into security domains. What I want to do is I want to think about this underlay fabric as being a single security domain, and my overlay to be a separate security domain, and then my app overlay to be a separate security domain separately again. So for instance, if I design my underlay such that the underlay cannot be attacked by any host or device that's attached to these top of rack switches, somehow I force it to bypass the underlay and only talk to the network overlay, that increases my security on this underlay fabric. So that is the type of thing that I can do. So what I want to do is, for instance, I want to use this modularization to increase security by allowing hosts and other applications and applications running on the host to only talk to one particular part of the network or one particular module. So now, for instance, if I look at this and I think I'm going to have these 2 hosts and they're going to be attached to top of rack switches, what happens if someone owns or roots this host and can then talk to the underlay in a way that can cause the entire fabric to fail? That would be a very, very, very bad thing. So what we can do here is, if I want to run routing on this host, then what I do is I only run the overlay. If I only run the overlay routing protocol or the overlay control plane on this host, then it would only have access to what? It would have access to its particular VLAN or its particular VRF or whatever you want to call it. It's Ethernet segment, it's ES, or whatever you want to call it in different control planes. And that's pretty much it. Well, it would have access to the other hosts that are also, or the other processes that are on that same ES or that same VLAN, but that's all it would have. It wouldn't have access to a lot of the other stuff that's out there, like the control plane for the underlay. It wouldn't be able to DDoS this router because while it has this physical connection, it doesn't have access to the right ports and stuff to get that. So the way that you deal with your routing on the control plane directly impacts the security of your data center fabric. So here is a point where my design and the way I have designed the network from a modularization point of view is actually directly impacting my security of the network. So it's very important to think about it in these terms. Another thing that's interesting to think about here is, if I have a single control plane in both the underlay and the overlay, and the host can talk to that control plane and take that control plane down in the overlay, it can, in theory, impact the underlay. Once again, if I've not thought through my modularization correctly, and both of these planes are running the same routing protocol, then I end up in a position where attacking this routing protocol also attacks this routing protocol. So I've actually merged the 2 failure domains, and I've also merged the 2 security domains. Now, of course, this is all going to depend on your implementation and how you've done things in your design. So again, this is something to think about when you're doing design, is whether or not you want to have these things combined or not. and how you spread them out and how you divide them from a modularization perspective. Now, another example is, let's say I'm running IS to IS in this network, and that's my underlay. And let's say I'm running BGP to run EVPN in my overlay. So that is my two protocols. So I've done total separation, and the host, let's say for some reason, can still talk to this router or this top of rack switch using IS to IS. Well, you might think, well, there's not a lot it can do. It can inject routes, things like this. But let's say that I'm very, very concerned about the speed of convergence in this network. So I tighten my ISIS timers down, way, way down, and I try to get it to converge in, say, 50 milliseconds or 100 milliseconds or whatever it is. So I tighten up everything, and I use exponential backoff for my timers so that I can force SPF to run very, very quickly the first time there's a change in the network, and then it runs more slowly over time as more changes take place. Well, if you think about it, if this host has access to IS, and I have tightly tuned timers, what this host can do without even knowing what routes to inject or what to do to bring the fabric down, it can simply slow down the convergence of the fabric by constantly injecting new LSPs in the network at the pace required to cause SPF to run more slowly across all of these devices. So what that's going to do is when there's a real change in the network, say this D2 to D1 link fails, these routers or these intermediate systems will converge much more slowly because they'll be running against their higher end of the top end of the exponential backoff in the network. So again, this is a situation where even if you split things up correctly, you've not thought through all of the attack surfaces in your design. So what you might want to do in this situation is to make sure this interface is a passive interface. Another point to make about this is another example of the state optimization surface trade-off, right? What I've done is I have tightly modified the convergence speed or tightly managed the convergence speed or optimized the convergence speed in this fabric to make it as fast as possible. But in doing so, what I've done is I've made myself extremely sensitive to the rate of the state that's in this fabric. So if somebody comes along and starts shoving state into this fabric really, really fast, it actually reduces my optimization by working against what I've optimized for. So this is, again, one of those situations where you have to think through, does my design really, really require this super fast convergence? Or am I okay slowing the convergence down in order to manage that attack surface? So we can think through how to use modularization and how to use network design to build security in, even before we get to the point of thinking about firewalls, stateful packet filters of various kinds, whatever it happens to be. I can actually think through my network and think through where I'm creating attack surfaces, where I'm doing interaction surfaces between modules, whether those modules are truly separated, or what I'm actually doing with those things in order to think through the security ramifications of my design before I deploy it and before I even get to packet filters. So again, to optimize, you either increase state or create new surfaces. And as I'm creating new surfaces or removing state, almost always leads to less optimization. So reducing complexity, one last point about this is that reducing complexity locally almost always increases complexity globally. So as I've decreased my complexity in each individual device or in each individual system, I'm actually increasing overall complexity globally. So I need to think through what I'm optimizing locally and globally and think through where I'm increasing complexity and go back to security, or complexity is the enemy of security. And I need to think about how I'm going to balance those things and make the network secure. So that is it. So I'll leave this open for questions. And this is just some other places you can find me if you're interested in some of my other work. It's my blog, my podcast, and my other podcast that you might want to listen to. Thanks for listening. And I hope this has been helpful in just connecting for you mentally the concept of security against the concept of design and giving you some pointers in how to think about design in a more secure way.
This was Russ White presenting on security and design. Russ White is well known in our community. Russ is an infrastructure architect at Juniper Networks and was just talking to us from Raleigh, North Carolina. This is Russ's seventh time presenting at NANOG. Russ first presented a talk called Trade-offs in Network Complexity at NANOG 60 in 2014 in Atlanta. Welcome back to NANOG, Russ, and we're certainly happy to have you back today. We're going to continue next with Q&A. First, there was a comment made about false sense of zoning, especially in a world where we tunnel anything through anything. Please comment.
So I was going to answer this in the chat window, but Joe, I know what you're saying, but I think the other way of looking at this is that when we tunnel, we actually are creating vertical domains in a sense. And that's what we want to do is we want to think about how to make those vertical domains or those vertically stacked domains into separate failure and security domains. It is difficult to think in terms of zoning as far as the WASP waste goes and everything from a hierarchical perspective or a topological method any longer, but to try to replace that a bit with a vertical stacked ways of doing things. So I hope that was helpful. Oh, good. Thanks, Joe. See your comment.
Very good. The next question that came up was about a use case where we would be doing an IGP, ISIS traffic inbound from a host port.
Yeah, so I've actually seen this in real life, which is why I put it in the slides. People who run either a single overlay or a single underlay plain IP underlay with no overlay, or they are actually running an overlay anyway, and then they are running IS to IS or something else to the host to run in the vRouter so that EVPN knows how to reach the correct next hops in the right way. I consider that really dangerous. I think you should always make sure that your fabric is protected as far as the control plane. The underlay fabric should be protected as far as the control plane goes from anything going on in the overlay or on the host, even on the vRouter. And I think that's just good failure domain separation and good hygiene in network design. So that's kind of.
Okay, thank you. Another question is, what other general rules to enhance security of the underlay would you recommend?
So one thing to think about is to encrypt your traffic across your own data center fabric. The problem with doing this is going to be key distribution and just the difficulty of configuring and managing an encryption system on top of a data center fabric. That is just very difficult to mess with or figure out how to do that. So, I've talked to some of I've talked to security folks who say you should be running MACsec on your data center fabric. Well, yeah, okay, but MACsec's very, very difficult to deploy, and it's very hard to think about how you would do that. So that is one of the general rules you can think about is how to just consider running some sort of encryption on your data center fabric to prevent insider attacks. Another one is just the whole concept of automation repeatability, making sure that you don't keep open ports, treating devices as part of the attack surface. Those, I think, are general things that you can think about as well that might be useful.
Thank you, Russ. What are your thoughts on BGP and the new external systematic dependencies introduced by the likes of RPKI?
Oh, so in a data center fabric, I don't know that I would think about pushing RPKI into my data center fabric. It's more of an external thing. As far as external dependencies go, well, I really have this thing about BGP and data center underlays that I actually don't like BGP as the underlay for a data center fabric because of some of the things we're doing to BGP and some of the externalities and stuff that go with it. So I'm not entirely certain that answers the question, but maybe if they want to continue, and let me see if I can see it.
Okay. What about what other material can a NANOG community reference to further learn about the design and security concept that you just covered?
Yeah, so I think probably the only place I've written about this in any way would be to think about is in network problems and solutions in computer networks. I don't tend to spend a lot of time talking about security, although I intend to spend more time in the security realm in the coming years. I saw a couple of other questions. I don't know if you want to do those, Ogi, or how much time we have.
Yeah, we have a minute left, but go ahead if you want to comment.
So Blake said something about abstractions are always leaky. Yes, that is the rule of leaky abstractions. And yes, it's absolutely true that all abstractions are leaky. And because they are leaky, you can end up in a situation where something like a DDoS attack in an upper layer can impact even a well-isolated lower layer. But of course, the more isolation you have, the less likely that is to happen. So that's why you need to think about reducing the depth and the breadth of the interaction surfaces. And then Blake asked also, how can one maintain loose coupling between layers in conjunction with differentiating between volumetric attacks and production traffic? Yeah, so the same sort of a thing, just thinking about the interaction surface between your layers as an attack surface. And I do like the idea, by the way, of pulling out fibers halfway. I think that's a really good idea.
That's cool. One final comment on complexity is the enemy of security. Final thoughts?
Yeah, that's absolutely true. This goes back to the first corollary of Keith's law, and that how important it is to reduce complexity as much as possible in a network to make it where you can get your head around things and understand what the side effects will be when you do something.
Okay, well, very good. Russ, we thank you very much for joining us. The NANOG community appreciates your time, and